You have now had some opportunities to work on some exponential problems that use logarithms to solve. We're going to take those problems a step further, talking about the concept of half-life and some other problems in exponential functions that involve proportions. So before we get into any of that half-life stuff, we're going to talk about some patterns in exponential functions that you've probably noticed in the problems that you've been solving. Once we get that out of the way, we're going to discuss half-life and exponential decay. We're going to take that a step further and discuss some similar concepts in other exponential function applications. And of course, we're going to work on a problem to show how these concepts can be put to work. So I want to talk about some things that you might have noticed about exponential functions, and just in case you've forgotten, an exponential function is of the form f of x equals constant a times constant b to the x power. So the first thing you probably noticed is whenever you had to plug in x equals 0, you got the value a for the result, and we're going to show you in this video why that works in general, but of course you've probably noticed that in a lot of the problems that you've been working on. And the second thing you may have noticed, especially when we were doing those interest problems, is whenever you had to find the interest rate, you just took whatever the b was and subtracted 1. And we're going to show you why taking that b and subtracting 1 represents either the percent increase or decrease of f of x when x increases by 1. You get a percent increase when b minus 1 is positive, and the percent decrease when b minus 1 is negative. So first of all, for the first one, let's look at what you actually get when you plug in x equals 0 into f. Well, if f of x equals a times b to the x, then f of 0 is a times b to the 0. And the nice thing about b to the 0 is it always gives you 1. So that always gives us a times 1, which equals a. And so, of course, that gives us a equals f of 0. And that's exactly why a is the initial value, f of 0, of our function. All right, so let's think about now the percent change when x changes by 1. And as you can tell, we're running out of room in this slide, so we're going to have to go to another one. So what I'm going to do is I'm going to look at what happens, say, when you plug in x equals some random value n, right? That gives you f of n equals a times b to the n. And if you add 1 to that, you get x equals n plus 1. That gives you f of n plus 1 equals a times b to the n plus 1. And if you want to know how much that changes, of course, you will subtract the two, right? You will subtract the latter one, a times b to the n plus 1, minus the one that comes before, a times b to the n. And if you want to make it so that they kind of look the same, the thing to remember is that if you take b to the n plus 1, that is exactly the same as taking b to the n and multiplying that by b, right? b to the n plus 1 means you're multiplying b by itself n plus 1 times. That is exactly the same as multiplying it n times and then multiplying it one more time. So you get a times b to the n times b for that first one, and then minus just plain old a times b to the n. And the nice thing about having it in this form is that you have a common factor of a times b to the n in both of them. So if you factor that out, you get a times b to the n times b minus 1, and just magically that b minus 1 appears, right? And what that means is, well, remember our f of n was a times b to the n. When we go from f of n to f of n plus 1, we get the value increases by a factor of b minus 1 over the original value at x equals n. In other words, the percent change per unit is b minus 1, where b minus 1 is that percent in decimal form, right? So if you have a 5% change, that b minus 1 is going to be 0.05, for instance. So that's why whenever you're finding a percent change, you always take that b and subtract 1 from it. So these are just some patterns that you probably noticed from the problems that you've been working on. And if you haven't noticed, here they are for you to use whenever it's useful to you. All right, so let's talk about half-life. So you may have heard the term half-life when it applies to radioactive material, about how fast it breaks down. So every radioactive material has a half-life. And not only is this true for radioactive material, it is true for any quantity that is going through exponential decay. And I'll explain what exponential decay is as well, but it all has to do with exponential functions. In fact, exponential decay happens whenever you have a function. I'm going to use t as my time as my independent variable this time. F of t equals a times b to the t, where your b is between 0 and 1. So these are the exponential functions that get smaller as time gets larger. And this is exactly what we mean by exponential decay when b is between 0 and 1. If you have b is bigger than 1, you have what is called exponential growth. All right, so the half-life of f is the amount of time it takes for the output of f to be half of the initial input. So, for instance, if your initial input is 10, it's the amount of time it takes for the output to get out to 5. If your initial is 30, it's the amount of time it takes to get to 15. And here are some observations about half-life as it applies to exponential functions. And these are things that are pretty astonishing if you don't think about them too carefully. So first of all, note that the half-life is an amount of time, right? It's the amount of time it takes for the output to be cut in half. Right, and when I'm talking about time, I'm talking about the input quantity. The input quantity in this case is t for time, but even if it were f of x, the half-life would be changes in the values of x. Right, and it's not the output, not the f of t, it's the t itself. So also, half-life represents the time necessary for another way of saying that something gets cut in half is it reduces by 50%. So if you have initial value and it reduces by 50%, half-life is the amount of time that it takes for that to happen. One of the weird things is the half-life does not depend on the initial value of f. For instance, if you have radioactive material, it takes the same amount of time for it to go from 100 pounds of radioactive material down to 50 as it does to go from 6 pounds to 3 pounds. The exact same amount of time. Counterintuitive, but that's just kind of how radioactive material works. And the other thing, and this is the one that is really kind of mind-blowing, is the half-life does not depend on what time you consider initial. Usually we think initial is time equals 0. So if I'm saying that the half-life of something is 5 years, yeah, that's the amount of time it takes between time equals 0 and time equals 5 to, that means between time equals 0 and time equals 5 years, it'll cut down by half. But it also works if you start at, say, time equals 6. So if you look at the amount that you have at time equals 6 and then go 5 more years to time equals 11, that will reduce by 50% as well. Not 50% from time equals 0, but 50% from time equals 6. So lots of weird things that happen when you talk about exponential functions, and that's just how exponential functions work. They're kind of miraculous little creatures. All right, so let's see how this works on a particular problem. So we're looking at a radioactive material, and let's assume that we know the radioactive material has a half-life of 3 years. That means whatever amount of material that you have in 3 years, you'll have half that amount of radioactive material. Question is, how long will it take for the radioactivity to reduce to 30% of the initial value? Right, so you get to half the initial value in 3 years. How long to get to 30%? Well, we know that radioactive decay is an exponential function. That means it's going to look like A of t equals constant A times b to the t. So here's the kind of sticky part of this problem. We don't know what the initial amount of material is. If you plug in time equals 0, we can't give a particular value of A. Right? So we can't find A directly. We're going to have to somehow solve this problem in another way. Well, let's not panic about what we don't know. We don't know about A, but there is some information that we do know, right? We do know that at time equals 3, that our amount of radioactive material is half of the original, right? Now, the original amount, the initial amount, is A, which we don't know, but half the amount is just 1/2 times that A. So that means after 3 years, in other words, at time equals 3, our A of t equals 1/2 A. So if we put in 1/2 A for A of t, and we plug in time equals 3 for t, we get 1/2 A equals A times b cubed. And now, some really interesting things happen. Notice that you have a factor of A on both sides of that equation. So if we divide by A on both sides of the equation, the A's disappear, and we end up with b cubed equals 1/2. And if we take the cube root of both sides, we get b equals the cube root of 1/2. So even though we don't know what the value of a is, knowing the half-life enables us to know what the value of b is. So our a of t equals a times cube root of 1/2 to the t power. We still don't know what a is. Hopefully that's not going to hurt us too much. All right, so the next slide, here's our function. A of t equals a times cube root of 1/2 to the t. We want to get down to 30% of the original amount. So what is 30% of the original amount? Well, remember, the original amount is little a, so 30% of that is going to be 0.3 times a. So we have 0.3 times a. We want that to equal a of t, which is a times cube root of 1/2 to the t power. And now we're going to solve for t. And notice once again we have a factor of a on both sides of that equation. So if we divide by a on both sides of that equation, the a's disappear. So we get 0.3 equals the cube root of 1/2 to the t power. Now we want to solve for t, so we can use some of our logarithm techniques, right? We can take the I like the natural log. If you like log base 10, that's fine with me. Take some kind of log of both sides, get log of 0.3 on the left side, log of the cube root of 1/2 to the t on the right-hand side. Now we can use our logarithm properties. Remember that logarithm property on the right-hand side means we can bring that t down outside the logarithm, right? And leave everything else alone. So we get ln of 0.3 equals t times ln of cube root of 1/2. Now we can divide both sides of that equation by ln of cube root of 1/2. And we get t equals ln of 0.3 divided by ln of cube root of 1/2. And that we can just plug into a calculator. We can plug it into Desmos. We can plug it into Wolfram Alpha. And we end up our t is 5.21 years. So if it takes 3 years to get down to half of the original amount, it takes about 5.21 years to get down to 30% of that. All right. Now, before I let you work on the activities, I do want to make one last observation, which may have just slipped by as you were watching that problem that we were working on. That t equals 5.21 years. That's the amount of time it takes to get down to 30% of the original quantity. And again, you may not have been thinking about this when we were solving this, but that is regardless of the original amount of the material. So if we wanted to be smart Alex about it, which of course I do, we could think of that 5.21 years as the 30% life of the material, right? 3 years is the half-life, 5.21 years is the 30% life, or the 0.3 life, right, of the material. And that sort of suggests that we can treat any percent change of the original amount in the same way we approach the half-life problem. If we know how long it takes to get to 30% of the original, we can solve the problem just like we did before. If we know how long it takes to get to 80% of the original, or 5% of the original, or 38% of the original, right? As long as we know how long it takes to get to whatever percent of the original quantity, we don't need to know how much the original quantity is in order to solve it, right? So for instance, if we know that it takes 7 years to get down to 60% of the original material, we can play that same game we played before by setting the 60% of the original material, that's 0.6 times a, and then plugging in time equals 7 into the function to get a times b to the 7th, and solve for b, right? And notice that in that equation, just like before when we were able to cancel out those a's by dividing both sides by a, we can do that in this equation as well. So some interesting things happening there. So you're going to explore some of these types of problems in the in-class activities where you're not necessarily dealing with half-life, but things that are very, very similar. And speaking of in-class activities, now's the time to start working on them. They're called half-life and related problems, and they're on the PDF file included with this video.